Creation of the universe is basically what we're talking about here, beginning in a true vacuum. So let's begin where we left off on the last video. We was proofing E, or at least arithmetizing it, a couple hundred digits deep. And we had these values at the end of our analysis. This is called a bottom quark. And multiples of a proton. And what we're going to get into in later videos, that this is actually, what I'm showing you is what they call the dark world. The dark energy, dark matter. We're going to the edge of human thought. So this is going to be a little bit different than anything you've been taught. It's going to have a different feel. So let's keep going. And then we had this at position 528. Which is a top quark. Okay, now every other one that we've ever done, we subtracted both of these. So let's see what we got. We've got a top quark and a bottom quark. 252. Now what is that? It's what I told you in pi, symmetry breaking. So where's the symmetry within 252? There's our 233, and there's 19. Well, what is 19? 19 is a lepton. It's an electron in a different family, and that is also pi. So anybody that thought this was a joke, this ain't no game, you know, we have a responsibility as a human race to get this right for the next generation. Okay, we have a lot of things confronting us. So spread the word, pay attention, and I appreciate your support. Okay, so you have the whole tie family right here. Okay, so to add some credence to this, let's divide pi straight up. Let's take pi divided by 9. Let's give it a relation right here. What any math professor will tell you at the bottom of math is basically adding and subtracting everything. Basically, when you're dividing, it's akin to subtracting. Now, what is this? This is the same, it's not, this is a proton. Okay? You have 2 up quarks and 1 down quark and a proton. Now you times that by 9. We divided by 9, so times it by 9. You have 15, 1, 2. And what is that? Take my symbol for 315, divide it in 150, 1, 2. and you got 48. Okay? Now let's divide it by 3. What do we got? No, that's our last one. And let's put a relation right here. That's 504. What is that? That's 16 times 315. Times that by 3, we got 48 again. Okay? And just to prove the point, take the square root of 48. And we took it basically 48 to the power of 1, 2. So we're adding which equals 48. 48 times my symbol for 315. Now, but what we're going to do today is, anybody that runs their mouth about they're going to give you 3 family of particles, they better bring it. So what we're going to do is we're going to start from scratch. We're going to go and I'm going to show you why gluon fields exist, what they are, and how they build a quark. And once again, we're going to look where symmetry breaks. And we're going to divide pi by 6. Okay. Divide pi by 6. And ultimately we're going to end up, let's put a relationship right here. Relation. Now what is this? Alright, now pi divided by 3 was perfect. Pi divided by 9 was perfect. What is this? 752. Okay. Let's write it like this. Okay. What I'm going to show you is I'm going to take these numbers and build all 3 family of particles and show you how the gluon mixes with the quarks to make the world and ourselves and human conscious what we have now. Okay. But first, I want to show you the 3 families of leptons. Now, leptons are basically electrons in different families. Now, we had the 6 when we proved to E. Okay? And times that gives a quark. So, this is its true nature pre-Big Bang as the vacuum is folding in on itself, unstable. And this is our Fibonacci sequence with our superposition that we showed earlier, beta radiation in the last one. Take this 74, which is a down quark, 60, 81. Now we have the muon family also. Okay, now let's divide the 74, which we use for beta radiation, which is 4727, and divide that into a muon quark and multiples of a proton, and you got 216. Now you take 810, 216. Remember the true vacuum, pre-Big Bang, the reason you got the universe we have. Okay, this is it. And let's add it. Okay, that's adding. Now let's subtract it. We got 4, 9, 5. Now take a value for electron. We are talking about electron is just in 3 families. Okay. Now let's divide by an electron. What we got? That's 19. That 19 is the value we just found in E. And divide it once again. 594. It's going to be 11. That is called a muon lepton. Okay. So we have everyday particles that everything we deal with in everyday life. Then we got the muon, and then you got the tie. Okay. Now we're going to take this, and we're going to take this, but first show why it exists, and we'll do some math to give us some evidence, because everybody's worrying about discovering things, but math is the highest standard of truth we have as human race. Math is discovered, numbers are created, as you can see. And this is how, that's why they're mathematical physicists. They dedicate their life to discovering physics through math. This is why, because it's extremely powerful. Okay. Now, with the gluon, you got something called chromodynamics. Frank Wilczek, stud, he discovered it. Back in the day, he won a Nobel Peace Prize for it. And what he discovered was atomic freedom. And basically what that is, forces usually get weaker the farther you go away. The farther the Earth is from the sun, less gravitational effect that it has. But quarks or gluon fields are different. When you're pulling them apart, the stronger they get. And the reason why that is the relations of the true vacuum. Okay? So as we was going through the Fibonacci, our rudimentary model that we made, okay, and we was going through this, and there's our, now these, as Frank Wilczek could tell you, in his book, which I read on Death Row, is these really do not mix, they borrow from each other to create an electromagnetic force. Okay? Here's our W and our B fields from the last video. Now, what we're going to do is take the first one is 2 relations. Alright? Let there be 2 relations. And that's a true vacuum, it's folding in on itself. And let's write this right here. Okay? Now let's go to 5. Let's go to 5. We have 13.8. Then let's end with this as being 7. Okay? So that's our 2, our 5, and our 7. Now, what we're going to do, let's add these. What is that? That's 16. It's a muon quark. What is this? That's an up quark. It's the first quark you got, smallest quark you have. Now, if you times these, you get 752. All right. Some evidence. You want to follow symmetry as much as possible throughout life, studying, you name it. Sunflower seeds, about the healthiest thing you can eat. You got the close to the Fibonacci spiral around it. You know, salmon got the beautiful layers of fat in it. Extremely healthy for you. Now we're going to take these, okay, let these be our gluon fields, which we're going to show how they gain mass and mix with the quarks to give you the values we have. Now if you remember, this 27 divided by 315 is our electron. So we're going to do that. That's 47. Then we're going to take a 5. And then we're going to take the muon lepton. There's our muon lepton. Then we're going to take the 7. And there, if you take away and do a evaluation, that right there leads to the tie. Okay? And actually this doubles. The 7 doubles. And I'll show you why. Number 1, if you take 47 times 16 is 63. And basically that'll be the radius instead of the diameter of 315. So that's why pi was showing us what it showed us when we did this. The universe will teach you. Math will teach you if you pay attention. That's what it was telling us, is going back here. Okay? And, you know, we got 37, 23 if you add up. Just treat them like pure ratios at this point. 37, 23. And that's our 6. Okay? But you have to do an evaluation to get the true one. But anyway, just where, you remember when I showed you where pi doubled? And we used that doubling, 266 times 2, to find our patterns in E. This right here doubles. And that's your muon. And it would double right here. It would double 14, or you can view it as a 315. It's the same way with electromagnetic force. You can view an up quark when we show beta radiation as 148, or you can show it like this. And we'll actually use that 101 to show Planck's constant a little bit later, and show the reason why a neutron weighs more than a proton. So they haven't figured that out, but we're going to figure it out. Okay. Now also, you will notice that the whole point, what the true vacuum is trying to do, and what every force's purpose is to get back to the state where it is equal. Okay? I showed you as the true vacuum has relations upon itself, that it carries the characteristics and traits. So it has that relation. That's what it's trying to get to. Right there. It's trying to get to even, basically. Now, how it's going to do that is, this is the whole thing behind the quarks. Because you have 20, 27, then you have a down quark, which is 20, 27, 27. And just give some evidence, although I got the mathematical proofs to show you. One time, if you want to dig down into it, send me a comment. Like me, not like me. You want to find out why you're here? Write a comment. Okay, you got the 14, 19, which is 33. And then you got the 14, 19, 19, which is your bottom cork. Okay, now, once again, what do we do, class? What do we look for? We look for symmetry breaking. Now you got 11, which is a muon cork. Well, that's not a strange cork. In the muon family, you got the charm, who don't love a muon cork, and then you got strange cork. Well, it is strange, although they didn't name it for that, because it's missing something. Because that's the true value of strange. And what we're going to do is, once I start getting, I'm going to build a proton, and then we're going to get into quantum gravity, and I'm going to show you a reason why that is. So don't forget it. So, and this is basically where you get your mass from. Okay? And if you try to pull these gluon fields, pull these corks apart, the stronger they're going to get. Because of why? Because the relations in the true vacuum. And that's what's going to happen. And basically what we're looking at is everything has a superconductor that makes it. Higgs boson superconductor. The only reason you exist is a Higgs field. Okay? You take a regular superconductor, electromagnetic, you got what you call copper pairs. And really what's going on in any kind of superconductor is, okay, we had all these relations, right? We had all these relations. But once it hits infinity, every relation is represented in the boundary. Because what did I tell you what affinity was in the last video? Affinity is just this. Affinity, it has no relations. Once you apply the relations, then you get what it really is. So a superconductor, you get it cold enough, and what happens is you have no relations. Okay? So what happens is the universe goes to work. It says, well, hell, we got to have these relations. What it does, it creates a magnetic field around here to represent that 315, and then it runs Cooper pairs, which is electrons around here, frictionless. And that's where you get most of your electricity from that we're doing this on. Okay? Now, at the bottom below the gluon fields, there's a gluon superconductor. Nobody in the world knows the reason it is. Frank Wilczek, my hero, he knew. He said, listen, where do the gluon fields come from? There has to be something that's creating these gluon fields, and that's what it is. And my postulate is it's at Planck length. Okay, and that ties into dark energy. We'll get into it. But basically what's going on is the true vacuum is doubling, which is a down quark times 2. Then you got the 16, which is a strange quark times 2. And then you got the tie, and we can do some math and basically show you the reason this is for some time. What is it? 104 minus 189, 158. All right, we got the 158, 851, I mean. And that's plus 189 equals 2 down quarks, okay? Now in our gluon rudimentary field, and I can go through multiple gluon fields and show you that they all have the symmetry, but this one's dear to my heart, so we're doing this one. And this comes over here. We have the 16, we have the 47. You add these together as we did before. And you got the 37, 20, 23. Now that's 60. You might say, yeah, that's a nice math, but you know, I need a little bit more. Well, if you dig hard enough and you study hard enough and you dedicate yourself to understanding the universe, the environment around you. As Hercules said, if you want to understand your environment, study many different subjects. Okay? Take 37 times 23. There's your 851. Okay? There's your 104. Now, all this is great. Okay? It's great. But you get most of your mass from this. So, I guess I better start showing you some mass equations, huh? Well, everybody knows this one, right? Einstein's famous equation. Here's some breaking news. This equation wasn't in his first paper. Okay, what it was, his instinct was correct. He put this one. And that's where you get your mass. Okay, so let's just give E the lowest value we can. Okay. I won't bother my math professor today and ask him to do the calculations I have written down. But what we got? 111,265. Take a 265. You can do many things with it, many analysis. I'm just doing this to show you a point. 376. What's 376? That's our 257. And that is your equation for mass. Now I want to do a couple things first. Let's go back to our model, because this is important. Because whoever's watching this, realize there's scientists all around busting their ass every day for you. Okay? So I'm doing this for them also. Because a lot of them work their whole damn lives trying to make a breakthrough and never do it. They die without seeing it. Okay? And no business would give me a business deal so I could go into the private sector and make the world a better place. So I'm doing this. It's like Einstein. He died in bed with pencil and paper in his hand trying to figure this out. He wanted to know the thoughts of God. And that's what I'm showing you. So have some respect for what you're seeing. Have some respect for the people that come before you. Now, I won't even get into the women that got no credit. And this is how it all started. I was on death row eating some sunflower seeds, which has a Fibonacci sequence. And I was watching this PBS. And there's this mathematician called Robinson on there. She solved Hilbert's 10th. Hilbert was a great mathematician during the time of Einstein. And he posed these problems for anybody to solve. She solved Hilbert's 10th with the Fibonacci equations. All right? And I was sitting in the cell thinking about her. I said, well, and what happened was she caught cancer. And matter of factly, she went out to the shed, got a shotgun and blew her brains out. And I was sitting on the cell in death row, and I said, a woman with that much grit, there has to be something to it. And then I looked at the sunflower seeds, which had the Fibonacci sequence, started thinking about it. So a lot of work goes into what I'm doing. And a lot of people sacrifice their lives. Because you got to be all in with this. You got to be all in. You know, I've been off death row a little bit over a year. I'm going to college. I got a 4.0 GPA. I'm working. To do this, you got to be all in. So I would appreciate y'all's support, because basically I'm working for you. If you're on this planet and you're a human being, I'm working for you. I'm a natural philosopher. I don't care what country you're from. I don't care who you are. I don't care if you like me or don't like me. I'm still going to work for you. Okay? Now, any mathematician will tell you this is undefined. Okay? And my math professor's looking at me crazy over here because I'm going over time, but I'm on a roll. So, here we go. I want to get into the Z boson and the W boson and show isospin. What basically isospin is the difference between the weight of the neutron and the proton, which I told you about, and you have some gluon isospin, but the really hard of it is the weak force isospin. So we're going to use this right here. Okay, now let's go down to our 144.89. Y'all remember this one? It's been good to us. Let's stick with it. Now, as I told you, with the neutrino, this right here, if y'all remember from the last video, if not, watch it. It creates, in beta radiation, the electron. Okay, now this is our neutrino. Now, neutrinos are funny. And it's the hardest damn thing I ever worked on in my life. Dark energy was the easiest for me. But neutrinos is a whole different ball game. But the real reason is this. They gain some mass, but they have to interact in a certain way to gain the mass. Nobody can figure it out. We're going to figure it out. Okay, so the neutrino, as you notice, has a 0 right there. Call this, we have something in physics that we call spin. Let this be the left-handed spin. Let this be the right-handed spin. Okay? Now, one of the great mysteries on Earth is why bacteria eats left-handed proteins and right-handed sugars. And I'm about to show you why. Now, this left-handed spin, it does not go all the way up. Y'all see that? Because the neutrino, that's 0. The B does. So we have the neutral W, which is the weak force, and we have neutral B, which is hyper, electricity. Okay? So if you add up all these, okay, this is our W, and this is our B. Okay. And interaction of these where you get the electromagnetic force from. Okay? So you have the left-handed spin and the right-handed spin. And this is the big reason how these neutrinos interact. The reason you have more particles than antiparticles. Okay? Because that's another great mystery. Why is there more particles than antiparticles? And this is really the heart of it right here. And you really can build off this 1, 0. It's undefined. Or call it dark. It's dark. It's there, but it don't interact with anything. Okay? I'll give you a perfect example. Try this out. Take any number. That's an N for any number. Raise it to the power. Raise it to the power of a true vacuum. What we start off with true vacuum. Every time it's going to give you this. Every damn time. What's missing? This is missing. Because it's dark. So anytime, that's why I was telling you in the last video, think for yourself. If there's something that exists in this universe, there is a reason for it. Okay? There's a reason it's undefined. There's a reason we'll get in uncertainty. Well, I'll get into it right now. I'll show you in philosophy the reason there's uncertainty. Well, if this is position, call this momentum. Okay, that's our first relation. Okay, now the uncertainty is Planck's constant. Once I prove Planck's constant, this will make sense to you, because in quantum mechanics, at this time in quantum mechanics, they cannot tell you the position or the momentum of a particle, and it has to have a certain degree of Planck's constant. That's the lowest it can be. And the reason that is because basically it's the same damn thing. If you look at a position or look at the momentum, you're basically looking at the same thing. You're looking at something that happened pre-Big Bang. That's why it has the characteristics or traits that it does. And it's really, if you study for yourself and really take time to investigate yourself, use a scientific method, and then you start to learn things. Now there are specialists are extremely important. We need experts in the world, but we also need people. Simon that started a theoretical physicist institution up there. I think it's called Premier in Canada. He calls us seers. You know, people that studied this on the edge of human thought. They really go to the edge. I mean, there's a lot, like everybody deals with infinities go crazy. Cantor went crazy, you know, but Cantor said one of the greatest sentences ever spoken. He said, infinity and created us all. He put his ass in the mental hospital, but I just showed you he was right. Because really what we're dealing with is the real number line. And anybody who's ever studied Cantor sets, E and pi make a real number line. Okay, we got 0, 1, 2, 3, 4, 5, 6, and then we go this way or that way. In his original papers, and Cantor says he showed E and pi create a real number line. What I show is that E and pi create the universe. Math is the language of the universe. Okay, now this 186 is a 301 that I promised you in my last video. And one thing, I take my word, my oath, and my promises seriously. Here's your 301 when we started off in E. Okay? Now let's start with the best isospin, and that's the weak force. Just isospin basically means difference, okay? You take a W boson, you got a minus and a plus W boson, which is 857 in multiples of proton. Then you take a Z boson, okay? 857 plus 115, and there's your Z boson. And here's the 115 right here. Now remember, this is a rudimentary model. And really, it should be taken it should be high tempered. The equations should be high tempered, but it's best to start off like this, so we get a full grasp of what we're dealing with, and then we get into the particulars. This is principle. This is my theory, union theory. It's copyrighted. You get around it, but it'd be just best to work with me. Send me a message. You know, let's make the world a better place for the next generation. All right. So basically, that's the 115. Okay. And this right here is your B. And you can do things like take that 188 times 4. What is that? 2? Yeah, there's that 752 right there. Okay, now to prove the point, we're going to take a proton and a neutron, and I'm going to show you the reason why the mass is different. But that's the whole thing about the bacteria eating left-handed proteins, left-handed proteins, right-handed sugars. that everything's about the true vacuum. And we're in a superconductor right now. And what the superconductor is creating what is missing, the relations that was missing. So that's the whole purpose of us being created. And in evolution, they teach you there's no purpose. They teach you a lot of things. But what I'm showing you that evolution does have purpose, and that is you. And the principle of evolution is consciousness. And we'll get into consciousness in the next video. And that's what Einstein wanted to know. He said, "To hell with the equations. I don't give. Yes, the equations are internal. Equations are but tell me the thoughts of God." That's what Einstein wanted to know. So that's what we're going to get into in honor of Einstein and other scientists that passed away without seeing this, without being able to work on this. Because I'm not the full package. I'm one human being. We survive all working together. Okay? So let's work together. And it doesn't make a damn if somebody has a different opinion of you, disagrees with you. That's the whole purpose of our existence. Evolution is not waste energy. It's going to create different people with different opinions to create a whole. Individualism is important. Now let me get into one thing real quick to just show you my point about math. There's this thing called wisdom of the crowd. And that's why we have democracy. If you look back, basically in England, that was the argument, was the wisdom of the crowd. And what that is, you take a jar of marbles and you walk through a crowd at a fair. And you ask each person to guess, how many marbles is there? And then you average them at the end. They're going to be perfect every time. Think about that. So basically you have a proton, and then you got a neutral neutron. And this is what the universe loves. It loves neutral. It loves getting back to equal. That's what it's all about. So you have the 101, and this up quark changes to a down quark. And you have that. And you have this. And if you remember this is what we got with pi divided by 9. Now the thing about it is let me show you something. This right here, this is human theory. And it's deep. Anybody want to work with me? Let me know. I got piles of notes I ain't put in this manuscript. Okay. Now the thing about it is if you take the values of a proton and neutron, not in multiples, of course, but if you take it and you really go and take the original, look it up, you can MIT has a value of the proton and neutron. This is some homework for you. Do it for yourself. And the digits go down. Well, you subtract them, it's 23. And why is it 23? The weak force isospin. That's what's going on. And with that, I'll say this. I've been free from death row over a year. I'm the first person in history to have both innocent projects. I like to do this full time. You have to be all in on this. I can't work 40, 50 hours a week, go to college, and do this. So I appreciate it. Anybody want to show me some support? I need some reliable transportation. I need some clothes. Anything, I would be honored to represent your brand and support me so I can support you. And at the end of the day, I'm going to tell you what happened. I got convicted, and the first words I said, evil just fracked with the wrong person, and I was going to hunt down evil and rip his guts out. That's what happened when that jury came back and said guilty. Those are the words I spoke. And that was my mission, and I learned evil dwells in human ignorance. But let me say this. It turned into love. Okay? When I was in that cell on death row, I did it for you. All right? Because I know if we don't solve these problems, you take the existence of the human race for granted. Neanderthals are considered a failure, and they was around 3 times longer than we are. So I appreciate your support. We live in a capitalist economy. Not that it's a bad thing. It has evolutionary traits to it. Can it be better? Of course. Let's make it better. Have a nice day. Keep love alive.